We look up at the night sky. We see stars. We see galaxies. We see the faint, milky glow of our own cosmic home. It feels infinite. But is it? There is a limit to what we can see. This limit is not a wall. It is not a barrier in space. It is a boundary in time. We call this boundary the edge of the observable universe. It is as far as light has had time to travel to us since the beginning of everything. Think of it like this. If the universe were a vast ocean, we are on a small boat. The horizon we see is not the end of the water. It is simply the limit of our sight from where we are, right now. Light travels fast, very fast, but space is vast, incredibly vast. The light from the most distant galaxies we can see has traveled for billions of years to reach our telescopes. When we look at these faint smudges of light, we are not seeing them as they are today. We are seeing them as they were in the distant past. We are looking back in time. The farther we look out into space, the deeper we peer into the past. It's a cosmic time machine, built not of gears and dials, but of light and distance. Every photon that strikes our detectors carries a story from a long-lost epoch. So, the edge of our universe is a temporal horizon. It is about 46.5 billion light-years away in any direction we look. That number might seem strange. If the universe is only about 13.8 billion years old, how can we see something farther away than 13.8 billion light-years? The answer is that space itself has been stretching the entire time that light has been traveling. The light from a distant galaxy has been on a journey through an expanding cosmos. It's like a runner on an expanding track. Our entire observable universe began with a single cataclysmic event. We call it the Big Bang. This was not an explosion in space, like a firecracker. It was an explosion of space. About 13.8 billion years ago, everything we can see, every star, every galaxy, every planet, every atom was compressed into an infinitesimally small, hot, dense point. Then, in a fraction of a second, it began to expand. This was the birth of space. It was the birth of time. It was the beginning of our cosmic story. In those first few moments, the universe was a chaotic soup of fundamental particles and energy. It was hotter and denser than the center of any star. As it expanded, it cooled. This cooling allowed things to start happening. Protons, neutrons. Then, after a few 100,000 years, the universe cooled enough for these particles to combine and form the first atoms. Hydrogen, helium. At this moment, the universe, which had been an opaque fog, suddenly became transparent. Light could finally travel freely through space for the first time. This first light is still traveling today. We can actually see the afterglow of this moment. It is called the cosmic microwave background, or CMB. It is the oldest light in the universe. When we point our radio telescopes to the empty spaces between stars and galaxies, we detect a faint, uniform glow. This is the remnant heat from the Big Bang, cooled over 13.8 billion years to just a few degrees above absolute zero. It is the baby picture of our universe. After the Big Bang, the universe did not just expand and stop. It kept going, and it is still expanding today. Every galaxy is, on average, moving away from every other galaxy. This is not because galaxies are flying through space. It is because the fabric of space itself is stretching. Imagine baking a loaf of raisin bread. As the dough rises, all the raisins move farther apart. No single raisin is moving through the dough. The dough itself is expanding and carrying the raisins with it. The raisins are galaxies. The dough is the universe. This cosmic expansion created the distance to the edge of our observable universe. The light from a very distant galaxy started its journey when the universe was much smaller, younger, and more compact. While that light traveled, the space it traveled through was stretching too. That stretching also stretches the light. This is redshift. The more distant a galaxy, the faster it appears to recede and the more redshifted its light. Measuring redshift is how we map the universe, our cosmic yardstick. By analyzing a galaxy's light, we see how much it's been stretched. That tells us how far away the galaxy is and how long its light has traveled. This principle, discovered by astronomers like Edwin Hubble in the early 20th century, revolutionized our view of the cosmos. It replaced a static, eternal universe with one that is dynamic, evolving, and has a history we read in light from distant stars. For a long time, we thought expansion might be slowing. Gravity pulls everything together. Perhaps it would reverse into a big crunch. But in the late 1990s, we discovered something astonishing. The expansion is not slowing, it's speeding up. Something is pushing the universe apart. As we studied galaxies, we noticed something strange. The stars on the outer edges of spiral galaxies were moving too fast. According to our understanding of gravity, based on all the visible matter we could see, the stars, the gas, the dust, these outer stars should be moving much more slowly. At the speeds they were traveling, they should have been flung off into intergalactic space long ago. The galaxies should have torn themselves apart. But they haven't. They are held together, stable and intact. This implies there must be more gravity than we can account for. There must be some kind of invisible matter that has mass and therefore exerts a gravitational pull. We call this mysterious substance dark matter. It is the invisible scaffolding of the cosmos. It forms vast invisible halos around galaxies and clusters of galaxies, providing the extra gravitational glue needed to hold them together. Its presence is the only way we can explain the motions we observe. We can't see dark matter directly. It is transparent. It doesn't interact with light at all, which is why our telescopes can't find it. We see its effects. We map its presence by observing how its gravity bends the light from more distant galaxies as it passes by, a phenomenon called gravitational lensing. These cosmic distortions allow us to create maps of where the invisible dark matter is located. If dark matter is the universe's invisible pull, there is also an invisible push. This is the force responsible for the accelerating expansion of the cosmos. We call this mysterious influence dark energy. We don't know what it is, but we can see what it does. It seems to be a property of space itself, a kind of energy inherent in the vacuum. Unlike gravity, which pulls things together and gets weaker with distance, dark energy seems to have the opposite effect. It pushes things apart, and it appears to be constant everywhere. As space expands, more space is created, and with it, more dark energy. This has profound implications for the future of the universe. It becomes more and more dominant over gravity. This is why the expansion is accelerating. This discovery earned its pioneers the Nobel Prize in Physics in 2011. Dark energy appears to make up about 68% of the universe. Dark matter roughly 27%. Ordinary matter a mere 5%. If the universe is the same everywhere, then beyond our cosmic bubble is also filled with dark energy, expanding and accelerating. Galaxies just beyond our horizon are being pushed away so fast that their light may never reach us. The edge of our observable universe is not just a boundary in space, but a receding frontier. If our universe is all there is, it is incredibly vast. But what if it isn't? What if our universe is just one of many? This is the idea behind the multiverse. It is not science fiction. It is a possibility that arises from some of our most advanced theories in physics. String theory, cosmic inflation. Cosmic inflation suggests our Big Bang was not unique. The same process could be happening all the time, creating countless other universes, like bubbles forming in a pot of boiling water. Each bubble universe could have different laws of physics. Most would be sterile and empty, unable to form stars or life. But with an infinite number, some will have the right Goldilocks conditions for galaxies, stars, and maybe conscious observers. It implies our universe's fine-tuning may be selection, not luck or design. This is the anthropic principle. For now, the multiverse is a hypothesis. Some search for bubble collision imprints in the CMB. So far, no evidence. It sits on the edge of scientific inquiry, a tantalizing glimpse of a cosmos far larger and stranger than we can imagine. Our quest to understand the universe is driven by our ability to see it, and our ability to see is constantly improving. Every new generation of telescopes opens a new window on the cosmos. allowing us to see farther, clearer, and in more detail than ever before. In recent years, telescopes like the Hubble Space Telescope have given us breathtaking views of distant galaxies, dying stars, and the birthplaces of new planets. They have helped us measure the expansion of the universe and have provided evidence for dark matter and dark energy. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built. It is designed to see the universe in infrared light, which is invisible to the human eye. This allows it to peer through the clouds of dust that obscure the view of other telescopes. Its primary mission is to capture the light from the very first stars and galaxies, looking back to the cosmic dawn. Early discoveries are stunning, galaxies more massive and mature than expected, challenging our models. Next-generation ground-based giants, the Extremely Large Telescope and the Giant Magellan Telescope, will push even further. They will analyze exoplanet atmospheres for signs of life and map dark matter with incredible precision. We are living through a revolution, and the future is even brighter. Despite our incredible new tools, there are fundamental limits to what we can see. The first and most obvious limit is the one we started with, the speed of light. We can only see the part of the universe from which light has had time to reach us. The universe beyond this observable horizon is, for now, completely invisible to us. And because of dark energy, much of it will remain invisible forever. The accelerating expansion of space is carrying distant galaxies away from us faster than the speed of light, meaning their light will never reach us. We are, in a sense, on a cosmic island, with the rest of the universe receding from our view. Another limit is the sensitivity of our instruments. Even within our observable universe, the most distant objects are incredibly faint. Their light has traveled for over 13 billion years, getting stretched and dimmed along the way. The James Webb Space Telescope is a marvel of engineering, but even it has its limits. There is a cosmic dark age, after the Big Bang but before the first stars ignited, almost impossible to observe directly. Dark matter and dark energy make up 95% of the universe, yet we cannot see them. It's like trying to understand a dark room by watching a few glowing dust motes. So, what is beyond the edge of the universe? The simplest, most honest answer is, we don't know. But the most likely answer is that it is simply more of the same. More space, more dark energy, more dark matter, more galaxies, stars, planets. Our observable universe is probably not special or unique, just one small visible patch in a much larger, perhaps infinite, cosmos. The physical laws and contents of the universe are likely the same out there as they are in here. There is no wall, no sign that says, the end. There is only the fading of our own vision. The quest to find out is one of the most powerful drivers of human civilization. It speaks to a fundamental part of our nature, the need to explore, the need to know what lies over the next hill, across the next ocean, beyond the next star. And so is our journey.